Thank you so much, James. And thank the organizers for the invitation to this wonderful workshop and this beautiful place. So in this talk, I'm going to tell you some recent results about in this van der Waals layered antiferromagnets, the surface magnetism actually orders at a higher temperature than the bulk antiferromagnetism, which is a very rare case. And then this is the science I'm going to cover. In addition, I want to show you that we have pushed the SHE sensitivity so that we can see both the order parameter and the quadratic of the order parameter that is proportional to the fluctuation of the order parameter. Okay, so let me start it by, thank the people. So the work is led by my student ZHAO, and then we had extensive collaborations to carry out this project. So the crystal was provided by Professor Ben Liu at UT Dallas, and then scanning transmission electron microscopy was done by Robert Houghton at Michigan, and then transport measurement were done by Lu Li at Michigan, and then we are also putting this material into photonic cavities, trying to see whether cavity can modulate its physical property, and that collaboration is done with Hui Deng at Michigan, and then theory has been done in collaboration with Kai Sun at Michigan, Igor Mason at George Mason University, and Harold Josky at Okayama University. So when we think about a real material, it's always of finite size. And when this is a fact, surface is ubiquitous. But then when we study or learn the phase transition in textbook, we always assumed our material is of infinite size and ignoring the presence of the surface. So it's actually a very interesting question to ask. What if we consider the surface presence in those materials where we have interactions and where we have spontaneous symmetry breaking phases? So this is actually a theoretical question that has been studied over the past 50 years. And then I'm trying to summarize their result in a simplified version, which is in this simplified cartoon phase diagram. So the horizontal axis is the relative strength between the effective interaction at the surface and the effective interaction in the bulk. And the y-axis is the temperature normalized to the effective interaction in the bulk. When the surface interaction is weaker than the bulk interaction, then as the temperature cools down, we only have one phase transition. And this is what we're familiar with. And this is the so-called ordinary phase transition since it's common. But when we look into the regime where the surface is actually stronger, has a stronger interaction than the bulk, it will happen in a situation that surface orders at higher temperature than the bulk orders. For the bulk onset, it's called the extraordinary phase transition, while for the surface, it's called surface transition. So those are the terminology in the theoretical literature. And then we can see the boundary of surface phase transition and the extraordinary phase transition merge at this point. At this point, they call it spatial point. So then there is a particular regime, temperature regime here that the surface orders, but bulk does not order. Okay. So then as experimentalists, we always ask, what are the realistic materials to see such a phenomenon? So we are trying to give a more intuitive illustration here. When we think about three-dimensional materials, we have interactions within the plane and between the plane. Because of the 3D nature, the interaction in the plane and between planes are nearly the same. So then when we consider the surface, for example, for a cubic lattice, the surface has only 5 neighbors, while the bulk has 6 neighbors. So we are missing 1 neighbor in this particular case. Then we have effectively 15% of less interaction strength at the surface. So it will require a lot of surface reconstruction to make up this missing neighbor at the surface, let alone to say overcome this effect and make surface to be even stronger. So then it's harder to see in the truly 3-dimensional system. But on the other hand, we can take a look at quasi-2D systems, where the in-plane interaction is way stronger than the interplane interactions. So then what is missing at the surface is just a very weak interplane interaction. So then imagine we have a little bit of reconstruction or some tuning in the surface. It can overcome this missing interaction and perhaps become even stronger at the surface than in the bulk. So then, like van der Waals materials is one example of this kind of quasi-2D system. And magnets is a kind of spontaneous phase transition. Yeah. So the talk is going to be focused on this particular compound, chrome sulfide bromide. I'm going to focus on the distinct transition temperature in the layers in this introduction that sort of hint us that the interaction in few layers could be stronger than in bulk, then hint us that this perhaps is the system we are looking for. And after that, I'm going to show you our experimental technique, which is second homogeneization that has been there for a long time. It's well known for probing non-central symmetric phases, but we are going to argue that we also have the possibility to probe central symmetric phases. And in this particular example of chrome sulfide bromide, we are actually having both central symmetric contribution and non-central symmetric contributions, and they interfere with each other. Okay, so let's get started. So chrome sulfide bromide is a van der Waals magnet, and its crystal structure is orthorhombic. Point group-wise, it has 3 mirror planes that are orthogonal to each other: mirror plane AB, mirror plane BC, and mirror plane AC. And then product of mirror planes leads to 2 photo-rotational symmetries along the crossing axis. So then 2-fold along ABC. And then together, product of 3 mirrors has inversion symmetry. Okay, so it's a central symmetric crystallographic material. And then magnetic point group-wise, if we look into the bulk, it has this kind of layered antiferromagnetism with a spin pointing in the same B direction within the layer and opposite B direction in between layers. So then, taking this into account, the magnetic point group is the so-called MMM1'. Here, all the point symmetries are exactly the same, MMM, and in addition to that, we emphasize the presence of time reversal symmetry in the bulk because if we do a time reversal operation by a translation of one lattice constant along c-axis, we restore the magnetic structure. And then this translation of one lattice constant in optical measurement, we cannot probe that. So then in the other word, we are saying the time reversal symmetry for this magnetic phase is effectively present for any optical measurements. And then we look at the surface. In surface, we naturally lose the mirrors that are parallel to the plane, and also we lose inversion symmetry. What's left over is a mirror plane, that is mirror AC, and then a mirror plane MBC together with a time reversal symmetry. This product is a symmetry operation. And then the 2 photo-rotational axes about C paired together with a time reversal symmetry is a symmetry operation. And yeah, that's the point group. So then we look into the literature. So in bulk measurements, there's a whole theory of literature here that in bulk measurement, once the temperature is cooling down, around 185, people start to see spin-spin correlation effect. And then cooling down even lower, around 155 Kelvin, there are debated interpretations. Columbia group assigned this one to be an incoherent c-axis ferromagnetism. Other group assigns to be short-range ordered ferromagnetism, also in the plane. Maybe, yeah. The difference is whether it's coherent within the plane or not between the 2 explanations. And then cooling down further, down to 132 Kelvin, that's the layered antiferromagnetism. So Columbia group did a measurement for 6 layers using second homogeneization. They see an onset around 138 Kelvin for the Néel order. And then they also have a result for bilayer. The onset temperature is 140 Kelvin, also from SIG measurement. And then furthermore, down to 1 layer, they see an even higher onset temperature, 146 Kelvin. So this trend is kind of clear that once you thin down, the temperature is increasing, which is counterintuitive and not present in many other 2D magnets. The usual case is that when you thin down, the temperature goes down. Yeah. Okay. So our technique.
Sorry.
Yeah.
Is this an XY? Is it easy in plane?
It's considered to be like Eisen type along b-axis because the lattice itself breaks the rotational symmetry in the plane and then spin-orbit coupling forces in this way. Yeah, but the spin gap is very small. It's only like 30 gigahertz-ish. Yeah. Okay, so second homogeneization. Traditionally, it's known that it's going to be absent if the inversion symmetry is present in the system. And this traditional knowledge is based on the assumption that we are considering only the leading order electric dipole contribution. As we mentioned in the morning's discussion that we know that there could be electric quadrupole contributions that can be present even when center of inversion is present. And also there's magnetic dipole contributions too, which is of the same rank as electric quadrupole contribution. Okay. So then in our measurement, we are going to do a full rotational anisotropic measurement, meaning that we are going to shine light at an oblique incidence and then collect light at the same oblique incidence. And then what we rotate is this scattering plane formed by the incident and outgoing light. And our polarization can be chosen in 4 possibilities: parallel to the scattering plane in and out, or normal to the scattering plane in and out. Parallel is termed as P, normal is termed as S. So then we have 4 channels. And since we are rotating the scattering plane with locked polarization, the operation itself is actually a fully symmetric operation. So then by looking at the data, if you see any loss of rotational symmetry, any loss of mirror normal to the sample, that's coming from the sample, not coming from the measurement itself. Okay? Okay, so that's sort of a cartoon of our experiment. The light is rotating, and then the data is taken in this polar plots. The radial distance just represents the intensity, and then the angle is just azimuthal angle. This is an example of gallium arsenide without center of inversion. So the signal is very strong, and it has 4-fold rotational symmetry that you see directly from the data. Yeah. So then, using SOG, such a traditional technique to study quantum materials, has been made effort by ETH like Manfred Fiebig in a lot of magnets, and more recently also by David Hsieh's group. So my time at Dave's group is trying to sort of push the sensitivity of this technique so that we can see very, very subtle non-central symmetric phases. And that has been done in iridates and cuprates back to my postdoc time in Dave's group. So then, when I started my own group at Michigan, we're trying to push the sensitivity a bit more to detect those central symmetric phases with a particular interest of measuring like electric dipole textures or magnetic dipole textures. So with progressive improvement, we can do both of them now. And in this particular talk, it's one more step to say that we want to measure not only autoparameter, but also autoparameter's quadratic terms. Okay. So then the experimental result. So because for a lot of van der Waals materials, people always worry about how good or how bad the crystal is. So how good or bad includes 2 aspects. One is whether we have like in-plane atomic defects. So then transmission electron microscopy looking into the plane confirms that for this crystal, there are very few defects atomically. And then another worry is that what about your C-axis stacking? Whether you have a lot of stacking faults along C-axis, that also creates complexity in understanding data. So they also can do, they means Professor Houghton's group, they can do the cross-sectional STM to verify that across multiple samplings of multiple samples, the stacking faults is very rare in the system. Perhaps because this is a overlay stacking. Layers are overlay on top of each other. You don't have multiple options anyway. So then there's very few stacking faults. Yeah. So then when we get the sample, we first do a heat capacity measurement in collaboration with Lu's group. In the heat capacity measurement, for the samples we can reproduce the 3 bulk sensitive signals, critical temperatures, 185 Kelvin, 155 Kelvin, and 131 Kelvin. 131 is just 1 degree lower than the literature. Yeah. So then what surprised us is that we just take a simple SHG measurement. We see an onset at 140 Kelvin on a bulk compound. This is a SHG measured at a 1 scattering angle and in 1 polarization channel. So just the intensity plot of SHG signal, which upturns at 140. So then this surprises us. So then we have to do a more careful measurement, which is this rotation anisotropy measurement. So in this measurement, if we do normal incidence, like this incident angle equals to 0, we see nothing. And this is expected because there's a 2-fold rotational symmetry along the outer plane direction that can fully suppress any SHG signal if you do normal incidence. But if we do oblique incidence, we can see clear data here. So these are the 4 channels at the incident angle of 13.5 degrees. So then if we look at all 4 channels, we can see 2-fold rotational symmetry present, 2 mirror present, and in fact, inversion symmetry is present by the inference of small signal level. So then our data is best fit by the electroquadrupolar contribution to SHG under this MMM point group. So you may ask, like, what about surface contribution, magnetic dipole contribution, and others? We rule out by saying that for those contributions solely, they cannot interpret our data. In the other word, we have to call for electroquadruple contribution to explain our data, but we cannot rule out the possibility others may be there, but then they themselves is not sufficient. Okay. Okay, so then we cool down the material down to low temperature. At 80 Kelvin, which is below the transition temperature, we can see the data looks like this, which is drastically different from the room temperature data. Okay, and then we can survey multiple samples, we can do multiple thermal cycles. There are only two options of the SH data below the transition temperature. And these two sets of data are actually related by the broken symmetries that we observe in the data. So then in the data, what we observe is that it still preserves this so-called AC mirrors. If we flip from the vertical direction, it reproduces. But it breaks this horizontal mirror that is parallel to B axis. And then it also breaks the true photorotational symmetry that is out of plane. So then the two domains, in principle, will just be related by the broken symmetries across this transition. So if you see the two domains, they are indeed related by a flipping along horizontal mirror and a rotation of 180 degrees. Okay. So then how do we understand our data? So then we said there are a few things in this compound. One is the crystallographic structure, which is this MMM point group, and we know that it contributes electroquadruple SHG. So then there is also this bulk antiferromagnetism, whose point group is MMM and time reversal. So this one has inversion symmetry. So then it, in principle, would have electroquadruple contribution to our data too. And then there is surface antiferromagnetism, which has this non-central symmetric point group M prime, M2 prime, which will give electric dipole SHG. So then if we look into their second-order nonlinear stability tensor form, the first two contributions, they will have exactly the same tensor form. So meaning that whenever we reduce the non-zero tensor element to this stability tensor, they will have the very same entries of non-zero tensor elements for the first two contributions. So then in our fit, we will just lump them together and then use a single tensor to fit the contributions of two. And then this one has a different contribution, okay? And then the experimental result at low temperature has to be interference of these three processes, which is essentially like mathematical interference of two processes, okay? So then we want to highlight a couple of things. Because the bulk antiferromagnetism has time reversal symmetry, so then the contribution from electroquadruple, which is time reversal symmetric, would be the same for the two domain cases. But for the surface antiferromagnetism, which breaks time reversal symmetry, then they will have opposite sign for the two domains. The two domains refer to left, right versus right, left. Okay, yeah. And then one more step. For the ones that are the same for the two domains, they should be proportional to order parameters even powers. For the ones that are sensitive to the domains, meaning with different signs of the domains, they should be proportional to even powers of order parameter. Okay, so yeah, the question would be that whether we can detect both contributions. So then we fit our data here. So the data is essentially fit in such a way. We have interference. So then electroquadruple contribution is in this first column here, and electric dipole contribution is in the second column here. For these like high temperature one, nothing in the second column. For the magnetic state, we have things in the second column. And the things in the second column are related by time reversal operation and two-fold rotational operation. And then the two columns interfere with each other to give the two possibilities of our data. So then we will do a harder work since we know how we can fit the data at low temperature. The harder work is just to do the flower pattern at every temperature and extract those optical stability tensors as a function of temperature, from which we can back out the order parameter information. Okay, so this is a force color plot of SH intensity in the SS channel. Vertical axis is angle and horizontal axis is temperature. Okay. If we do a horizontal cut, that will be a plot like this, where you can see the onset. If we do vertical cut at selective temperatures, you can see the evolution of the flower pattern as a function of temperature. Okay. So the fitted result is showing here. So the first line here, the first figure here, is showing the electric dipole contribution. And the second line here is showing the electric quadrupole contribution. And the last line is the magnetic stability measurement done on exactly the same sample that we did the optical measurements. Yeah. So we can clearly see for the bulk sensitive magnetic stability measurement, you only see one feature, that is 131, the bulk phase transition temperature. And then for this like electric dipole contribution, that's mainly coming from the surface antiferromagnetism. Its onset temperature is actually at 140 Kelvin, which you can see from here. Yeah, 140 Kelvin. That is about 9 Kelvin higher than the bulk transition temperature measured on the same sample. And what's more interesting is the second column. If we look at this other parameters even power term, we can see more features. The signal starts to degrade around 185 Kelvin, and then has a steeper decrease around 155 Kelvin, and then a weak divergent behavior around 140 Kelvin, and then another kink around 132 Kelvin. So then this is because like when there are spin fluctuations or correlations that happening at the temperature scale between 140 and 185, the autoparameter quadratic term is actually sensitive to the spin fluctuations there. And that's why they can capture the 185, 150 onset temperatures. Okay. And then for the bulk transition, it's just when bulk orders, it will also back react to the surface and give a slight kink in the surface magnetism here. Okay. So yeah, so then our result is sort of show we add one more temperature scale in this bulk sample, and this temperature scale is happily coincident with bilayers onset temperature. And we term this one through our measurement as a surface phase transition, and then this one is extraordinary phase transition at 131 Kelvin in our sample. So this is one experimental demonstration. So then we work together with theorists to understand what might be the possibility to make this happen. So the theorists calculated 4 scenarios for us. So the first scenario is a bare bulk, and a rigid monolayer means that they just take a monolayer out of the bulk without any relaxation. Okay? By just doing so, you can see the onset temperature already can increase. So their interpretation here is that there is a intralayer exchange coupling who has a exchange path that goes through the next layer. And that is actually antiferromagnetic. So then that cancels the intralayer ferromagnetic coupling. So this is their interpretation. And then they did the third case, which is they take a layer out, but then they fix the lattice constant, but allow intra-unit cell relaxation. After doing that, you can see there's another jump of the critical temperature. And this is to say that the fine-tuning of the intra-unit cell structure can also help increase the magnetic onset temperature. And then lastly, they did a free monolayer, meaning that they allow it to freely relax. That will suppress the transition temperature. Okay. So with that, I hope I showed the science that, we demonstrate this is a rare phenomenon, but it happens in a 2D magnets. And then for this kind of situation, perhaps it's actually more general than we thought. We just have to have this technique that is both sensitive to surface and sensitive to bulk. And it might be an interesting system if people want to think about non-equilibrium driving into such a system, because this system, the fluctuation range is actually pretty wide, and surface order is different from the bulk. Yeah. And then technical-wise, we hope that we provide a probe that is possible to be integrated together with non-equilibrium driving controls. Because we can combine with strain, we can combine with current, we can combine with cavity, and combine with electromagnetic wave illumination. Yeah, and we have the sensitivity to both autoparameter and also fluctuations. So perhaps the integration in the future could be interesting. With that, thank you so much for your time.